Right. I think with this session, last time we probably discussed bulletproofs as a polynomial commitment scheme. Correct me if I'm wrong. So bulletproof slash IPA, people will also call it polynomial commitment. And I think today we're going to discuss KZG commitments, KZG polynomial commitments. And the other session is one meeting ahead because I had to cancel a meeting a couple weeks ago just on Friday, unfortunately. So we'll have to sync them back up again. Okay, can someone confirm that that's right and that you can see my screen?
Yeah, I can see your screen.
Great. Okay, so just as a summary of the cost of bulletproofs, so the commitment size is just a Peterson vector commitment to basically the coefficients of the committed polynomial. So the commitment size is just one group element. Okay. With any polynomial commitment scheme, the verifier has to be able to, after it receives the commitment, like go back to the prover and say, hey, I need to evaluate the committed polynomial at this particular point. Tell me the evaluation and prove to me that the evaluation you're telling me is correct. Is consistent with the committed polynomial. So in bulletproofs, the evaluation proof has size log n. And however, so that's pretty good. That's actually the best among non-recursive and transparent commitment schemes. But the verifier time to check that proof is n group exponentiations, which people call linear time. It's actually worse than that. So it's concretely, it's something like 400 times n group operations. It's actually asymptotically superlinear. People are, they sort of say negatively that the bulletproof verifier is linear time. They're actually underselling the runtime when they say that. And so proofs are short, but verifier is slow. Now, a couple, sort of counterpoints. And by the way, not only is the verifier slow, the prover is just as slow as the verifier for the evaluation proofs. So it's also n group exponentiations. Actually, I think it's 2n for both of them. But anyway, counterpoint. As with any homomorphic commitment scheme, the cost of evaluation proofs can be amortized effectively. So if you commit to many polynomials and need to evaluate them at, each at either the same point or different points, you can kind of have the verifier like combine all those commitments to different polynomials into one commitment and kind of have one evaluation proof for all of them. So you pay this expensive cost only once. And so, in some applications, in some settings, it makes sense to be able to, you're able to do this amortization. And then while, the prover and verifier are really slow for these evaluation proofs, that significantly mitigates the badness of that. Okay, so I guess that's the summary of bulletproofs. Does anyone want to ask anything about that? Okay, so let's talk about KZG. Briefly, here are the pros and cons of KZG. So a con is it's not transparent, unlike bulletproofs. Okay, so that is what's called a trusted setup is needed to generate there are different terms for it. You can call it a proving key, you can call it a commitment key, you can call it a structured reference string. Okay, what is that that key, that structured reference string? So basically, someone has to choose a random exponent tau exponent meaning if we're in a multiplicative group, so working over a multiplicative group. So as with bulletproofs, KZG commitment scheme, the commitment turns out to be a Peterson vector commitment. So it uses a cryptographic group, and I'm going to use multiplication notation to denote the group operation. And so the structured reference string for KZG commitments is called powers of tau, and you stick powers of tau in the exponent of some group element. So the string is g to the tau squared up to g to the tau to the n, if you want to commit to degree n polynomials. Okay, and so the key point is that anyone who knows tau can break binding of KZG commitments. And so when KZG commitments are used in a snark, if you can break binding of the commitment scheme, then you can typically break the snark, which means you can find convincing proofs of false statements. And so it's essential, it's like basically, in a sense, someone has to know tau to generate this SRS, and then they have to forget tau. Because if they don't forget tau, then they could act as a cheating prover for the snark. Okay, now in practice, we have ways of basically, you could say generate the SRS via what's called MPC. Okay, what that means is, like many different people can contribute to, the SRS, so to like randomizing tau. And, unless all of them get together and, to reconstruct tau, no one will know anything about tau. Okay, and like Ethereum actually just ran this kind of people call this a ceremony, a trusted setup ceremony. Ethereum just ran a powers of tau ceremony with like many thousands of participants because they're interested in using KZG commitments at the base layer for something called data availability sampling. So the N they used is like way too small for use in snarks. With snarks, the prover just has to commit to bigger polynomials than what the SRS that Ethereum just generated supports. But KZG polynomial commitments are useful, like not only in snarks, it turns out. And the point is that if like enough people generate the SRS together, and you can do it one after the other. So anyone who participated like knows as long as they themselves threw away their like share of tau. You think of each person who participated as having like a share of tau. And as long as, if you participated and you throw away your share of tau, for sure that no one knows tau. And anyone who didn't participate, as long as they trust that, at least one of the participants threw away their share of tau, everything's fine. And so, for a lot of people, such as Ethereum itself, the whole community, I guess you get enough people to participate and they seem comfortable, assuming that not 100% of the participants all got together and reconstructed the tau. By the way, tau, if I didn't say it, is called toxic waste. Anyone who knows it can destroy security of the scheme. So that's what I have to say, I guess, about the trust assumption like baked into an SRS. But there are performance implications for having this SRS as well. In particular, if in order to make this SRS big enough for use in a lot of snarks, it will wind up being like many gigabytes in size. So people have generated SRSs that's certainly at least as big as like a dozen gigabytes or something. And anyone who wants to act as the prover, the snark prover, anyone who wants to prove things needs to download it. Okay, so that's a nuisance. Like if you if you want the prover to run in a browser, you really can't have the prover downloading and storing a 14 gigabyte, string or something. So it does limit the size of the circuits that people can apply snarks to. Yeah, I mean, it might not be the biggest deal, given that but people gotten pretty good at recursion. So you can typically break a big computation up into many small pieces and prove each piece separately and somehow aggregate the results. But nonetheless, like it's clearly limiting, even from a performance standpoint, to have this big string that anyone who wants to act as a prover has to download. So it's not just like a trust assumption that some people don't like. It's also has performance implications. So that is a downside of KZG relative to bulletproofs. So with bulletproofs, like the commitment key was a bunch of random group elements. So just completely random group elements. This key, is just as big as the KZG key. But I guess the point is the way you would generate the bulletproofs key is you would just like take a cryptographic PRG, pseudorandom generator, and evaluate it on some like agreed upon seed phrase. So you wouldn't have to download from some repository or something like a 14 gigabyte string. You could generate the string locally. And it's also possible in some application, like maybe you don't have to at any point know the entire string all at once. I'm not sure about that. I have to think about that. But anyway, so bulletproof has a similar issue, but it's not as bad because the string can basically be generated locally with a PRG if it's just a bunch of random group elements. Whereas if it's not random group elements, but rather there's one random exponent tau and all the group elements are derived from tau in some way, then people have to, and no one can know tau, then people have to just download each and every one of these group elements. Okay, so that's bad for KZG relative to bulletproofs. Good is the evaluation proofs are smaller, and faster to check. So with bulletproofs, again, they were logarithmic size, which is pretty small, but slow to check. With KZG, there are constant number of group elements. Let's just say order 1 group elements. We'll see later today, depending on the variant of KZG you use, I think it's either 1 or 2 group elements. And the verifier time is something like 2 pairing computations. And I'll say shortly what pairings are. So basically, KZG has better verifier costs. Okay, but is not transparent. Okay, the KZG prover, by the way, is like a little bit faster than bulletproof. So like the commitments, to compute the commitments, it's sort of the same for both bulletproofs and KZG because it's both just the Peterson vector commitment. It's both just what's called a multi-exponentiation, also known as an MSM, multi-exponentiation of size n for both of them. But the evaluation proofs for people, this is like not well appreciated. The evaluation proofs for KZG is also like 1 MSM of size n for KZG, whereas for bulletproofs it's n group exponentiations. It's really 2n, but for the compute the evaluation proofs, this is actually substantially slower than an MSM of size n. This is like it could be up to like 20x slower. So this is not, I don't think this is widely appreciated. Like I think people would have to actually run both KZG and bulletproofs, like opening like evaluation proofs to recognize that there's like a 20x difference in the computation time for them, but there is. Okay, let me think. Is that all I wanted to say about the cost of KZG? Yeah. Okay. So one more bad thing. It's not a huge deal, but bulletproofs doesn't need a pairing friendly group. KZG does. So this is bad for KZG. So bulletproofs doesn't need pairings. KZG does. I'll say what pairings are shortly. But basically, some cryptographic groups, that people use are pairing friendly. Others are not. So groups that are not pairing friendly. Let me just list some popular not pairing friendly groups. So there's something called curve 25519. It's like it's a curve with very fast, group operations, but it's not pairing friendly. There's something called pasta curves. People like these because they're very recursion friendly. So I think next time we meet, we'll be talking about recursion. Um, Pasta curves are recursion friendly. It's what's called a cycle of curves. If you don't know what that is, don't worry about it right now. The Zcash folks have developed a very high performance implementation of pasta curves. They are not pairing friendly. Um, let's see, I'm pretty sure the curve that Ethereum and Bitcoin use for digital signatures, which is SecP something or other, is also not pairing friendly. Maybe that's a good list. I'm struggling to come up with others that are important. So these are not pairing friendly curves. What are examples of pairing friendly curves? So in the Ethereum community, by far the most important is BN254. This is the only curve that's an Ethereum precompile. So even if you use a snark that doesn't need pairings, in Ethereum you would still at least want the verifier. You would still want that snark to be defined over this curve because you want on Ethereum you want any on-chain verifier that should be if it's doing group operations, then the group operations you want to be from this group, BN254 operations, because the fact that it's a precompile means the gas fees are just astronomically lower than if you used a different group. Okay, so unfortunately, shortly after Ethereum declared this curve to be a precompile, slightly better attacks were discovered to compute discrete logarithms in this group. So it was initially thought to have close to 128 bits of security, but when the better attacks were discovered, it became clear it doesn't have close to 128 bits of security. Now it's this weird situation where it's a little hard to tell just how efficient the attacks are. They're still way too expensive to actually run. So there's some debate about just how efficient the attacks are. But a conservative estimate now is that the attacks take over 2 to the 100 operations. So basically, people now consider this curve to have 100 to 110 bits of security. And I'd say 100 is quite conservative in terms of estimating how expensive the attacks are. That means the attacks take at least 2 to the 100 steps, to compute, discrete logarithms or whatever. And I guess 110 is maybe a little bit of a more aggressive assumption, saying, it doesn't seem like the attack, can be implemented really faster than 2 to the 110 steps, but it's not 100% clear or something like that. So if you still want 128 bits of security or close to that, which, I think we should aim for, then I'd say the most popular pairing-friendly curve today is something called BLS 12381. Now, this gets disparaged a bit for performance reasons because 254, I'm pretty sure, refers to the fact that BN254 is sort of defined over a field. Remember, like elliptic curves, the group elements in elliptic curve groups are pairs of field elements satisfying a certain equation, like y squared equals like ax cubed plus bx plus c or something like that. I don't even quite remember the equation. So it's pairs of field elements x, y satisfying this property. And if you tell me, a, b, and c, you've told me the curve. So you change a, b, or c, you've changed the elliptic curve group. And I think the 254 and BN254 refers to the fact that this field is of size about 2 to the 254. Whereas with BLS 12381, I think that field has size about 2 to the 381, which just means that it takes a little bit more space to write down each group element. It's 2 381-bit things instead of 2 254-bit things or whatever. And it's a little bit slower than to do the group operations and stuff. But there are some very highly optimized implementations of BLS 12381. I think Supranational has a really nice one, which maybe they've even tried to formally verify the correctness of and stuff. So if you go outside the Ethereum community, I'd say this is the most popular pairing-friendly curve now, because people do want 128 bits of security, and outside of the Ethereum community, you're not sort of stuck with this precompile of BN254. In fact, even in Ethereum, I think data availability sampling is going to wind up using this curve. It's going to be some weird situation, at least initially, where the base layer will use this curve to do data availability sampling, but smart contracts will not be given full access to the group operations from this curve. So if you're a Solidity developer, you still sort of can't use this curve, so people designing snarks are still not going to wind up using this curve, even though Ethereum will be using it at the base layer, according to the roadmap, once data availability sampling is enabled. Okay, so I think that's maybe enough for now about different curves and which ones. I'm not listing all the curves out there that people use, but in short, some of them support pairings and others don't. At least a little bit of a performance price if you want a pairing-friendly curve. Again, BLS 12381 operations are a little bit slower, certainly than curve 25519 say. You can expect them to be at least 2x slower. I hear differing estimates. It might be more than 2x. Okay, so let me just pause there. I'd say that's a brief summary of kind of the comparison of bulletproofs and KZG. Again, pros of KZG: better verification costs, faster computation of evaluation proofs. Cons: it needs a trusted setup and it uses pairings. Any questions? Okay. Can someone just confirm that I haven't dropped off the call or anything?
Yep, you're still there.
Okay, great. Thanks. All right, so let's talk about what is a pairing. So I think the right way to motivate it, we talked not that long ago about Peterson commitments, right? And a Peterson commitment, if you forget about blinding factors, to commit to X, a Peterson commitment to X is just G to the X. Yeah, you just stick X in the exponent of a group generator, and you sort of think of X as kind of being hidden in the exponent, where unless you can compute discrete logarithms efficiently, if I tell you G to the X, there's computing X requires solving the discrete logarithm problem, basically. So the prover who chose X knows the exponent, but kind of no one else does, something like that. Okay. And I talked about how, via homomorphism, we could take commitments to two different values, say X and Y. And, so without knowing X, given only G to the X and G to the Y, without knowing X and Y, we can nonetheless compute a commitment to their sum. So by multiplying those two commitments together, you can get G to the X plus Y, right? So just by multiplying those two commitments together. So in that way, you can get a commitment to the sum without knowing the two individual, what the values inside the two individual commitments. Okay, but I said there wasn't an analog of this for multiplication. So I said, let's say the prover has committed to X, Y, and Z. Okay, and the prover wants, claims that, Z equals X times Y. So I said, there's not an analog of you can't check this claim directly, or you can't get a whatever. What I said, what I gave you was a zero knowledge proof of knowledge that indeed Z equals X times Y. So without revealing, so this was a Sigma protocol. I didn't cover the details, but I told you, it's in the book, and it looks analogous. It looks similar to Schnorr's Sigma protocol. And so, there's a relatively efficient way the prover, given these three commitments, could prove that the third commitment is a commitment to, the product of the values inside the first two commitments. But the prover has to actually, provide a proof. Okay, with pairings, you can actually do this check without the prover's help. So pairings do let you do this check. Let the verifier check this without the prover's help. Without P, proving it. And so here's what goes on. So in a general pairing-friendly group, there's actually three different groups. So G1, G2, and what's called GT. T stands for target group. Okay. Now the book assumes that G1 equals G2. That's just for notational simplicity. If G1 equals G2, it's called a symmetric pairing. Now, in practice, pairings are not symmetric. There are symmetric pairings known, but they are much slower. The group operations are much slower in those groups. So in practice, people will use asymmetric pairings. So in this lecture, I guess I'll discuss, I'll separate G1 and G2, say they're different groups, but the book, just calls them both G. It just assumes it's a symmetric pairing. That's just so we don't have to keep track of two different groups, G1 and G2. Okay, so what is it? What is a pairing? A pairing is another name for what's called a bilinear map that maps elements of G1 and G2 to the target group. Yeah. And what bilinear means is the following. It means that for any, let's see, how do I want to say this? For any exponents A and B, the map is bilinear if E of G to the A, comma G to the B. Okay, sorry, I guess if you have two different groups, then this G should be an element of group 1. And this G should be an element of group 2, because the bilinear map, takes one element of group 1 and one element of group 2. But for symmetric pairing, I would write G and G here rather than G1 and G2. So if E of G1 to the A, comma G1 to the B equals E of just G1, comma G2 raised to the power A times B. Okay, and what that means is, and you can maybe think about this a little offline, but basically, if I'm given three group elements, say G to the X, G to the Y, G to the Z, and I want to check, without knowing any X, Y, and Z, I want to check if X times Y equals Z. I can. The following is equivalent, so I can check that. E of G to the X, comma G to the Y equals E of G, comma G to the Z. Okay. Maybe I should just say, let's let's assume there's always a trivial bilinear map that just maps everything to the identity element of the target group. So let's assume E is not trivial. By trivial, the trivial map would just be defined as E of anything equals the identity element of the target group. Okay, and that'll trivially satisfy this property because under this definition, E of G1 to the A, G2 to the B is of course is just one, which is the same as E of G1, comma G2, which is also by definition just one, to anything. So the trivial map that just maps everything to one is bilinear, but not interesting. So assuming it's not the trivial map, then you can check that bilinearity of E tells you that X times Y equals Z if and only if this property holds right here. Okay. Now, computing the bilinear map is fairly expensive. So you don't want to have a snark verifier do a huge number of pairings, right? In Gross 16, which is sort of the snark with the fastest known verifier. The verifier does like 3 pairings. So it evaluates E, 3 times. Like that's fine. Like that's good cost for the verifier. But if the verifier had to do like many thousands of pairings, right? Like let's just say 1,000 pairings, right? Like 1,000 isn't like a huge number for computers. My computer can do billions of operations a second, so 1,000 isn't much. But 1,000 pairings, like that's pretty expensive. I actually should look up roughly how many group operations is equivalent to 1 pairing. But anyway, so a pairing is like way more expensive certainly than just like 1 group multiplication.
And anyone else still here?
Like how, what is the structured reference string? So, in order to commit to a polynomial, the committer needs to know this key where somebody picks a random exponent tau. So you think of it as remember, you think of it as like a random field element. Remember, like exponents of group elements without loss of generality, they live between 0 and the size of the group. Okay. And the size of these elliptic curve groups is typically like a large prime. And so this set is like, for any prime, there's, the integers modulo that prime is a field. And so that is called the scalar field of the elliptic curve group. If this prime is, if the size of the group is P, then the scalar field is all integers modulo P. So tau is chosen. I can call it a random exponent. I call a random element in the scalar field. And the structured reference string, that the committer needs to know is all powers of tau in the exponent. Yeah. And up to this here, n is the degree of the polynomial you want to commit to. And actually, yeah. So that's the commitment key. Okay. And in order to commit to a polynomial, say p of x is the sum from I equals 0 to n of ci times x to the I. The commitment is just so let c be the vector of coefficients, and the commitment is the commitment to the polynomial is just the Peterson vector commitment of C with this commitment key. So since I'm using multiplicative group notation today, that would be the group product, I equals 0 to n of g to the tau to the I to the ci. So this is like the I SRS entry raised to the power, the ith coefficient of the committed polynomial. And as a result, what this commitment actually is you're literally just evaluating the polynomial that you want to commit in the exponent, right? So you can just do a little algebra, right? Like taking g to the tau to the I and raising it to the power ci is the same as multiplying tau to the I by ci. And then this big group product just sums all those up in the exponent, right? So it's sum from I equals 0 to n of ci times tau to the I. Yeah, so the commitment to P is literally just evaluate P at tau in the exponent, right? And so the SRS is letting the prover evaluate the polynomial it wants to commit at tau in the exponent without knowing tau. Okay, so yeah, so in words, the commitment to P, the KZG commitment, is the evaluation of P at tau in the exponent, of G. And the SRS lets the prover compute that commitment, that is, evaluate P at tau in the exponent, without knowing tau. No one knows tau. Because so basically, because there's an S, like that's why we need the SRS, is to let the prover evaluate the committed polynomial at tau in the exponent without telling the prover what tau is. Okay. One remark. So bulletproofs actually is a commitment scheme that directly applies not just to univariate polynomials but to multivariate ones as well. KZG is very specific to univariate. So there are ways that are known to transform any univariate commitment scheme like KZG to a multivariate one, but those transformations introduce some overhead. Okay, so that's sort of another benefit I'd say of bulletproofs is as a commitment scheme. So both Fry and KZG are specific to univariate polynomials, and you'd have to pay a performance overhead to turn them into multivariate polynomial commitments. Bulletproofs and some others apply directly to multivariate ones in addition to univariate ones. So just a remark there. Okay, so that's the commitment for KZG. Okay, let me pause here. Does anyone want to ask a question?
Is there a limit for the what's a good way to put it? Do you have pairings on smaller fields, or are they all relatively large fields?
Yeah, so I'd say okay, so for any elliptic curve group, pairing friendly or not, for discrete logarithms to take at least 2 to the 128 steps, to compute, the field has to be a size at least 2 to the 256, just because there's a generic algorithm that in a group of size, if the group size is 2 to the k, the algorithm computes discrete logs in size 2 to the k over in the number of steps equal to 2 to the k over 2. So that's why any cryptographic group you ever see, the field is always at least 256 bits, because 256 over 2 is 128, and we aim for 128 bits of security typically. So BN254, had fields of about 256 bits. People might, skimp on just 1 bit of security or something, which is why this is 4 and not 6. But it turned out that better attacks were discovered. So now on that particular curve. So now, as far as I know, if you want a pairing friendly curve at 128 bits of security, it's not known how to do it with a 256-bit field. You do have to go to a slightly bigger field. But it's not night and day to go from 256 to 381 bits. It's bigger, it's meaningful, but it's not an order of magnitude worse or anything like that. Does that make sense?
Yeah, I'm kind of curious. With small fields, could you use an extension field to find a pairing, or is that not possible?
Yeah, that's a really good question. Okay, so I don't offhand, I don't know the answer. I'd have to look it up. What I know about elliptic curves over extension fields is there are elliptic curves in which we think discrete logs are hard to compute over extension fields. Several years ago, maybe I don't know, 5 to 7, 8 years ago, there were surprising better attacks discovered on some of those curves, which sort of freaked some people out. And so some people just avoid any elliptic curves defined over extension fields. But there are elliptic curves defined over extension fields, where the field is still reasonably small, where the best known attacks do take time, 2 to the 128. So, it's a little bit debatable. People differ in terms of how, sketchy they think, the security of using elliptic curves over extension fields are. I do not know whether the curves I just referred to are pairing friendly or not. My guess is they can be, but that's a guess. I'd have to look it up.
Thank you.
Yeah, I'll try to follow up about that. But I'm just gonna go to Google and like Google like elliptic curves extension field pairings or something and see what I can come up with. Yeah. Cool. Other questions? All right. Okay. So that's the commitment. So now the question is just the evaluation proof. And actually, let me pull up my notes just to make sure I don't mess this up. Just take a second. So the evaluation proofs, they're pretty. What's going on is like pretty intuitive, but like, I just want to make sure when I try to cover like a sketch of the formal analysis that I don't make any silly mistakes. So let's see. Bear with me. I'm sorry, I should have pulled these up. I was running late today. All right. Okay, so so here's the idea. So there's a fact. The fact is that for any degree n polynomial p, let's say p of r equals v, if and only if there exists some, call it a witness polynomial, w of degree n minus 1, such that, what's the equality? P of x minus v equals w of x times x minus r. Okay, so at least one direction this is really easy to see, which is if p of r equals v, that implies that the left-hand side here equals 0 at r. And similarly, this factor x minus r ensures that obviously the right-hand side equals 0 at r. Okay. And so, yeah, in particular, so that tells you the direction that I guess if you can write p of x minus v in this form, then clearly p of r equals v, because that's the only way the left-hand side is going to evaluate to 0 at r, but the right-hand side definitely evaluates to 0 at r. Right? So that's one direction of the implication. The other direction just amounts to that you can like always factor out roots of a polynomial. So if a polynomial, if it feels like algebraically closed or whatever, so like all roots of any polynomial like exist in the field, you can always write any degree n polynomial as like a product over all of its roots. Let's say it has n roots, n plus 1 roots, I guess. Well, yeah, I think n roots, whatever. Sorry, I'm very sleep deprived today. You can always write it as x minus like its roots. I don't know. Let me call it, zi, where z1 to zn are its roots. Again, I'm blanking on whether I guess a degree 2 polynomial has 2 roots. So yeah, degree n is going to have n roots. So yeah, let's start this from 1. Anyway, so yeah, that's sort of saying, so if p of x if p of r does equal v, then p of x minus v, then r is a root of p of x minus v, which tells you that you can like factor out that root from p, and that's like where the other direction of the implication comes. Okay, questions about that? So this is the main property of like univariate polynomials that KZG exploits, and there are analogous properties satisfied by multivariate polynomials, but they're just grosser in certain ways that wind up when you try to exploit those properties to give an analog of KZG for multilinear polynomials, the resulting verification costs go up and things like that. So that's why I say KZG is very specific to univariate. We actually don't know without using recursion like an analog of KZG for multilinear polynomials with constant size evaluation proofs. The size of the evaluation proofs that we know of kind of grow with the number of variables of the polynomial we want to commit. And these multilinear polynomials that some check-based snarks like to use the number of variables tends to be logarithmic in the size of the circuit you're, proving a statement about. And so rather than having a constant cost verifier, you have a logarithmic cost verifier. So that's why I say KZG commitments quite specific to univariate ones, unlike bullet proofs, which sort of just directly applies to both with no kind of transformations needed. Okay, so the rough idea of KZG is the following. So to prove that P of R equals V, the prover, sends, and by sends I really means commits to, also with KZG commitments, W. Okay, and then the verifier wants to check or needs to check to check that P of R equals V. The verifier needs to check that that's equivalent to, or checking this equality holds is equivalent to checking that. So the verifier wants to check that. Let me call this equality star. That star holds. So that is P of X minus V equals W of X times X minus R, where W is the polynomial the prover committed to. Okay, and it's the way it's going to do that is it's going to probabilistically check that this equality holds specifically at the random point tau, right? So intuitively, this is how we always, if you want to check that two equalities are the same, if you've been with the group from the start, you've seen this 1,000 times. Always, what you do is you just evaluate, the two different polynomials at the same point. And if they agree, you're comfortable that indeed they're the same polynomial, right? Because two distinct low-degree polynomials can't agree on any points. So the prover would have to get very lucky if the random points you evaluated them both at happens to be one of the few they agree at if they're not the same polynomial. So the intuition is that no one knows tau. So tau was chosen at random by some party that later threw away tau. So it's random, but no one knows it. And so it's like okay to it's like safe to spot check this equality at tau. It's just like saying, hey, the prover sent these two polynomials, is claiming they're the same polynomial. Let's just check whether they agree at tau, and if so, it's safe to believe they're the same polynomial. Okay, so that's the intuition, and how does the verifier check that? Okay, well, checking that the equality holds at tau, let me just write it out. It's P of tau minus V equals W of tau times tau minus R. Okay, so what we're going to do, surprise, surprise, is we're going to use pairings, right? So the verifier doesn't know P of tau, but the commitment to P put P of tau in the exponent. So the verifier does know P of tau in the exponent. It doesn't know P of tau, but it knows the group element obtained by putting P of tau in the exponent. Okay, the verifier does know V directly because the prover is claiming, hey, P of R equals V, right? Like, so the prover is just telling the verifier V, right? It's, V is the value that the prover claims P of R equals. Okay. W of tau, also the verifier doesn't know because the prover only committed to W. It didn't actually send W, but the commitment to W is just W of tau in the exponent. So V knows W of tau. And V also V does not know R. V does not know tau, but it does know. So the verifier does need what's called the verification key, which is just like two group elements, G and G to the tau. Remember, the SRS that the prover has to know had all n powers of tau in the exponent. For verification, the verifier only really needs to know one power of tau in the exponent. So V does not know tau, but P does know G to the tau. And V explicitly knows R. That's the point that the verifier requested the evaluation of P at. Okay, so that's what P knows. So in summary, that's what the verifier knows. So while it doesn't know P of tau, W of tau, or tau, it does know each of them in the exponent. Okay, so in order to check that this equality holds, this is what we're going to do. We're going to look at, we're going to apply the pairing to, let's see. Let's do it this way. So we've got our G to the P of tau, so this is just like, the commitment to P. And we're going to multiply it by G to the V, which the verifier knows knows V. So in the exponent, that's just adding V to tau in order to get this, P of tau minus V in the exponent. Oh, sorry, that should be the inverse of that, because we want to subtract V from P of tau. We don't want to add V to P of tau. And then it's also going to feed into the pairing W of tau. Right, that's the commitment to W. And then G to the tau, again, this is part of the verification key, times, I guess, G to the R inverse, right? And so the pairing is, this is equivalent to checking that, P of tau minus V, which is sort of what's going on in the exponent on the left-hand side here, equals W of tau times tau minus R. Did I do that right? It's X minus R, right? Yeah, times tau minus R. Which is exactly equivalent to confirming that equation I called star before holds at tau. Okay, so that's KZG commitments. Like that's how they work. So you see the proof, the evaluation proof is just the commitment to W, and the verifier just does two pairing evaluations. Okay, any questions about that? Cool. Okay, so let's talk a little bit about formal security. I mean, basically, you now understand KZG commitments, and you can just assume what I just said is like that scheme is a polynomial commitment scheme, and like basically you'll be fine. And so if that's what you're interested in, how KZG commitments work. You literally can leave if you'd like. But let's talk a bit about security, like proving it formally. Okay, it gets a little bit nuanced. So the scheme I just described to you is it's actually not quite a polynomial commitment scheme. If your security proof, let's say, unless your security analysis is done in an idealized model, like let's say done in something called the algebraic group model or something. So I'll explain more about this in a bit. So based on like standard assumptions in like a non-idealized model, the scheme I just gave you is it satisfies what I call function binding. So basically, for any point, once the prover commits to P, so for any requested evaluation point R, there's at most one value V, such that the prover can produce a convincing evaluation proof. Okay. So it sounds like the prover is bound to. Okay, so it means the prover's, after the prover commits to P, it is bound to like some function, meaning, it's not the case that when the verifier requests P of R, that it gets to like pick and choose, like what the claimed value it returns is, right? So as soon as the verifier has the commitment in its hand, for any evaluation point R requested by the verifier, there's only like one value the prover can respond successfully with to the verifier's evaluation query. So that means like the prover cannot change P after it sends the commitment, right? As soon as that commitment's in the verifier's hands, for each requested evaluation, there's like a unique value the prover can open, can reveal there. So it can't, the committed polynomial cannot be changed after the commitment is sent. The issue is that there's no guarantee, according to the security analysis, that these values that that the committed function is a degree n polynomial. So there's no guarantee that there's a degree n polynomial such that, you know, these values lie on the polynomial. So in principle, like, we can't rule out, we can't rule out that, it's just some like crazy function that the prover is bound to. The prover sends, the KZG commitments to something that's ostensibly a degree n polynomial. And while it can't change the function that it's now bound to, it's possible that the function it's now bound to is not itself a degree n polynomial.
Yes,
That's
sir.
what I'm trying to say.
Sluggish.
Okay.
It's crazy. As I'm going older,
And so I'm going to go through that security proof in a moment, but it only establishes function binding,
game changing.
not evaluate, not that the proof is bound to a degree n polynomial, which is what we really want in our
How many
stars.
hours?
So in order to show that the prover is actually bound to a degree n polynomial, you either need to do your security analysis in an idealized model, or you need to alter the scheme so it's a little bit more expensive. Okay, so I'll maybe mumble a little bit about those alterations shortly. But let's just see why function binding holds. And I'll be a little sketchy here. But and I've already sort of presented the scheme in a way that hopefully suggested it should be secure. But I think sketching the actual security analysis is a little bit helpful. So this is the part that I want to make sure I don't mess up. So let me
just so used to working at like 60% capacity that they think they're fine, because that doesn't make sense.
Yeah, maybe.
Even though Elon Musk does that. Elon Musk gets like
How many?
I think somewhere like 5.
Really?
Yeah, I think he gets like he doesn't get too
okay,
much.
So I guess
Like also Elon is a specimen.
it's a little bit.
He's like basically made in the lab.
I still find it a little bit hard to present the formal analysis, like the intuition
Yeah,
that goes through each step of the formal analysis. But
all right.
so imagine
I
that
have some pretty good news.
Okay.
P.
All right, so
Imagine that P of R did not equal V. Okay, in that case, this equality star does not hold. So there is no degree n minus 1 polynomial for which P of x minus V equals W of x times x minus R. Okay, so another way, I guess, of saying that is that if P of x does not equal V, then P of x minus V over x minus R is not a degree n minus 1 polynomial.
It was made by Meta and like 2 other studios.
This is the intuition. So if like the prover actually committed to a degree n polynomial,
really cool.
but it's not the case that P of x minus V, P of R equals V, then this ratio will not be a degree n minus 1 polynomial, because otherwise there would be a degree n minus 1 polynomial such that it's
We can get ideas from there.
okay, and
exactly. Their website for sick, mainly
yet
the as I was going through
verifier winds up ultimately checking that
which is
so the prover does wind up committing to some degree n minus 1 polynomial,
there's
call
at one point
W prime. So the prover does commit to a degree n minus 1 polynomial
with
W
mixed
prime.
reality, because like you had to have your spatial setup. I think it's if you haven't
and
done
the verifier
it's
checks that P,
it's
that the equality holds at tau, so it checks
so
that
like
P of tau minus V over tau minus R
would become like the cockpit of a
okay,
spaceship.
so if
and like
this thing is not a degree n minus 1 polynomial, but the prover sent a degree n minus 1
that became like
polynomial,
the backside of the spaceship.
it feels like I'm getting myself
was that
little
the room went dark.
confused here. It feels like there's no way.
It went dark.
So basically the verifier, the prover would have to get lucky, in terms of tau, just because if W prime is low degree, but this thing is not low degree, like roughly speaking, you can't show this formally, but
It was like the lights in my room.
these two functions should disagree at many places.
And so I was like, well, why
and
don't
so
we
the
fucking
prover,
do that?
intuitively would have to get lucky.
Like, I didn't even realize that was possible.
For them to
Yeah.
In
agree at
WebXR,
tau.
that you could like, dim the experience. There's another game where it's called
How do I want to
Cubism.
say this?
actually kind
Once
of
the
funny and
prover
fun. It's
commits
literally
to,
just like
W prime,
spatial puzzles.
I'm a fan of Cubism.
okay, so what's going on
Oh,
is
you know, yeah, I
to
love
get
that
to the
game.
chase,
I
since
actually
I'm
just
not
started
doing a very
playing
good
it
job here.
yesterday. It was
It
really
feels
fun.
like
I was just lying in bed playing.
to make this
I
check
used to
pass, it
play
feels like the
with,
prover it needs to
Quest
be able
2
to divide
VR.
P of tau
I
minus
actually
V.
like it more
by
in
tau
VR
minus
than
V.
in MXR.
Okay,
Mixed
that's
reality,
the key
because
point.
in AR,
Like to get this
you're
equality to
immersed,
pass,
in
that
a
the verifier
wide
checks
ocean.
with the pairings,
So you,
you
it's like
need to
relaxing.
Effectively
Plus-
ensure that P of tau
I
minus
I
V divided by
was
tau
interested in
minus
like
V
the pass
equals
through when I saw it.
something
because
else
I
that
was
the
just like
prover sent
lying in my
that
bed.
is low degree
It was sick, but
evaluated
I'll
at
have to try
tau.
VR
That
next
seems
time.
to require like dividing by tau
Because the
minus
hand
V.
tracking's amazing too.
That's the key point.
Like, it's
So
really good.
there is a cryptographic assumption
But
that
nonetheless,
basically
yeah,
just
I
assumes
realized you
that
could also dim the
dividing by
brightness
tau
in
minus
that
V
as well.
in the exponent is
pass-through.
hard.
You could even change the
Okay.
contrast. Yeah, it was like you could
Right.
change
So
the brightness,
it's
the
saying like, look,
contrast, and the
the prover
saturation.
knows this SRS that
And
has
the thing is,
powers of
I
tau in the
assumed
exponent.
last night that was like, oh, it's just because like
The assumption
doing it
is
natively.
that
or they're going through Unreal
that
Unity.
doesn't help the
Right,
prover
but then when I tried this
divide
demo
by
today, the
any
spatial
simple function of
fusion
tau
one,
in the exponent. Right.
it
So
made the whole room go dark.
the SRS
And so
lets the
what are your thoughts
prover
on doing
evaluate
that? Like, I think that would
any
completely solve our
simple
fog
functions
problem.
of
And
positive
if not
powers
even
of
better,
tau in the exponents.
have the
Such as G
user,
of P of tau. Right. This
use
is
a
a
flashlight?
weighted sum
yes,
I like that.
of positive powers
Sounds
of
cool.
tau.
I'll send
Ci
you
times tau to the I. These are all positive powers of
it's a
tau. But
4-minute
dividing
video, so
by
it's
tau
actually
minus
kind of
V
steep.
is
Sounds cool,
this is
and
like
you know what
this is a
else?
negative power of tau. After
We could
subtracting by V.
also
So it feels like the SRS,
send to the backend,
by
not just
revealing
the
to the prover
position of the
positive
head
towers,
of the
positive
user,
towers of
but also the
tau in the
direction of the
exponent,
light.
should not help the prover
So
multiply by a
the-
negative power of tau in the
The
exponent.
answer
And so
from the backend
this
relating,
assumption
the position
is
of the
called
object,
the strong.
takes into account also
What's it called? D
where the
strong.
user is,
I'll say N strong
aiming
Diffie-Hellman.
the light to. At.
Yeah, totally. Yeah, we could totally do that.
Okay. And so formally the assumption is
because I wonder if like because if you're just like spamming your flashlight around, whatever,
the
even just that
SRS, which
alone,
has
but
these
like
positive
if you're
powers
holding
of
your
tau
flashlight
in
on
the
it for like 2
exponents,
seconds,
it is
fuck it.
intractable
I
to
think
output.
I think the flashlight idea is sick.
Yeah.
Like I didn't know you could do that.
And do you already know
Let's
how to do
say
it's
a
simply
V
just a
and
spotlight on
a
your hand.
group
You know how I
element
have the pointer set up,
of the form G to
right?
the
Like
1
how you could
over
extend
tau
in
minus V.
meta gallery. You're
Okay,
able to
so this is like a way of
and,
formalizing that
bring
even
back
though the
the
exponent
pointer for
like
anything you're
told
holding.
the prover a bunch of positive powers
Right,
of
that's
tau.
based off
Sorry,
the
the SRS told
orientation
the
of the
prover a bunch of
controller.
positive powers of tau in the
So
exponent.
literally all that would be
That's
is
not
essentially
helpful
that.
in having the
It is the
prover
orientation
compute
of
a
that
negative
controller,
power
and
of tau in the exponent.
it's just like a spotlight.
And so this is an assumption that
that
actually
you would place
predates
right at the
TCG
edge of the
commitments.
controller. So instead of the pointer, it's just the spotlight.
I can't say too much. So it's from a 1997 it's from a
It's sick.
2004
But the only
paper,
thing
but
is that,
is analogous to a
I don't
related
know
assumption from a
how to do the
1997
background,
paper.
but like I didn't look into it at all.
So the
like
KZG
how to
commitments
dim
came
it.
about after both of
It
these
kind of like
papers.
blew my mind when that happened.
And
I was
so
like,
yeah, I
where's
mean
this light coming
it's
from?
intuitively like very
I recorded
plausible
the whole thing.
that if I tell
and I
you
was like, where's
positive
this
powers
light
of
coming
tau
from?
in the
And then I realized it pointed
exponents,
at my wall, and I was like,
but
wait
discrete
a second,
logs are hard to
what the
compute in this
fuck? I was
group.
like, what?
So telling you,
do that?
these group
I got
elements
so
shouldn't tell you
excited.
anything about
It's like
tau.
instantly correlated to
That
this.
they also
Is
shouldn't be
their
helpful
source code
in
available?
sort of computing a
No,
negative
I
power
love
of tau in the
Polio.
exponent. Very plausible.
It's
I
not-
can't
I
say
looked
much
up-
more than
I
that
mean,
for
I don't
why
know.
cryptographers
Were you
have
able to find it?
sort of coalesced around this
I have
assumption
no luck.
as like a very reasonable, safe one. But
It's cool.
it
There's like a
feels
shared VR
natural
button at
enough
the
to
top
me.
left, right? So like, that's how
Now,
I
of
started
course,
it.
this
It
is
was, like,
a
perfect.
stronger assumption than that discrete logarithms are hard to compute.
Yeah, I wish they had the
Because
short
if
ones. I
discrete
really-
logarithms were
that'd be
easy to
awesome.
compute, then anyone who reads the SRS could
Yeah,
pull
I
tau
guess,
out of the exponent. So the SRS has
I
g to the
guess
tau. If you could solve discrete log, you could
there
solve
has
for
to be
tau,
some
and then
documentation
obviously
about that
it would be
somewhere,
easy to compute
perhaps.
g to the 1
Yeah,
over tau
guys,
minus
the
v.
fact
If
that
you
they
know
did
tau,
it
then it's
means
easy to
it's
compute 1 over
possible.
tau minus v, and then
Like,
you
that's
just
the
raise
only
g to
thing
the
I need to
power.
know.
So this
That's
is a
it.
stronger
Like,
assumption
I
than the
didn't think
discrete
it was
logarithm
possible.
being hard,
But now that I realize you
but
could, like, dig
very,
the
very
environment,
reasonable, considered a
now it's
mild
just a matter of
assumption.
finding.
Okay, and so the intuition is that
Interesting. Do you see the font
again, to
they use?
basically open a KZG proof, KZG commitment up to two different values,
Is this
two
the
different
font we chose?
evaluations at the same
I'm sorry?
evaluation point. Like the only way to
The
do
font
that
they use?
is,
The font
the
for
verifier is going
spatial
to basically
fusion
check
logo?
that this holds.
Is that the one we used?
No.
The only way to do
it
that,
happens to
this
be
check is
the
being done in the
font
exponent.
that
So roughly,
I
it feels like the only way to do
for
that
the
is to be
logo
able
of
to
my
divide p of tau
company,
minus v
for
by
example.
tau minus v all in the
Oh,
exponent.
really?
It's exactly the same
Okay,
font.
that would violate
Oh,
this
shit.
I don't
n-strong
remember the
Diffie-Hellman
name,
assumption.
but yeah, that
And
A
so,
with a point in the center,
what
that
we formally need to
gives it
show
away.
is that,
Which one are you looking at?
so suppose,
Spatialfusion.io.
P can convert,
The
the prover can
Oh, I see.
produce,
Yeah, like the main title.
a convincing
So this
KZG
is the
evaluation
webpage
proof.
for
Both
my
for both that P of R
and
equals
you can see
V
the A
and
there.
P of R
It's the same A.
equals V prime.
Mm.
Okay. We
That's
have to then
interesting.
show formally that this
We took
means
your idea. We
you can
should-
break the D-strong
we gotta take
Diffie-Hellman
it back.
assumption. We have to show that this implies you can compute,
But yeah, sadly,
let's
wasn't able to
say,
get the assisted
V
space
comma G to
set
the
up
1 over
going. I
tau
don't really
minus V,
understand how that works,
something like
but
that.
hold on.
Okay,
For one
so I'm
second.
going to explain why that's the case. I'm going to do it sort of with a bit of intuition, I guess. Won't be completely formal. Again, I hope this. I'm not doing the best presentation here, but I hope it's helpful enough. So the verifier
So
sort of
this
checks
guy
all in the
from
exponent
Spatialfusion, we
that remember
can say
v checks
they are our
in the exponent that q of tau, for this
Definitely.
proof to pass. V checks that
Exactly.
q of
Not
tau,
maybe
p of
illusion,
tau minus
but like
v
they,
equals
I
w
mean,
of tau.
inevitably
This
it will
is
be them
the witness
too,
that
but
the
they're
prover
more
committed to
based
in
on
the
just
first
like
proof
general immersion, like
when
3D
claiming that the value is
browser.
v
But the other one, what's their name?
times tau minus
I see.
r.
Spatialfusion is not a
So
company.
that's the check in the first proof, all done in the
No,
exponent.
it's
The
made
check
by
in the
Foria,
second proof,
Illusion, and Meta.
all done in the exponent, is that
So
p of
this is
tau minus
Foria.
v
The one I just
equals
sent
w
you.
prime
in
of
XR
tau, where
Studio.
this is the committed
The other one, Illusion, is
degree
the,
n minus one
they're more
polynomial
like web design,
committed with
but
this polynomial for the second proof
their
for the
website's
claim
really cool.
that
Like their website's
p of r equals v prime
Foria is just like pretty standard
times tau minus r.
when it comes to like.
So
I guess
the verifier checks both of these
Studio.
qualities hold, but everything's in the exponent. So really,
But still, it's really cool.
It's really checking g
They
to
do.
the
But yeah,
left hand
so I would
side
say
equals g to the right hand
Foria
side.
is our
For
competitor.
both of them.
But also they're in fucking Australia. So.
And so,
The world is very large.
but if you just look at the
Exactly.
exponents,
Definitely
like
has
what we
room
have
for
here
another
is two,
Yeah,
basically
especially
two
something
linearly
that's
independent equations in two unknowns.
Yeah,
And so you can just solve for the unknowns. So in a little more detail, if you I'll just do the algebra. If you subtract the two equations from each other, so subtracting these two left-hand sides from each other, what you get is the first one minus the second one is v prime minus v, right? Because the p of tau's cancel if you subtract these two equations from each other. And then the right-hand side, if you subtract the two equations from each other, what you get is w of tau minus w prime of tau.
But nice, yeah. Nonetheless, so
times tau minus r.
He held the background.
And so you can simply, what do you do now? I'm trying to solve for 1 over tau minus r. So you can divide both sides by tau minus r and divide both sides by v prime minus v, and you get that 1 over tau minus r equals w of tau minus w prime of tau over v prime minus v. Great. And so remember the prover, sent, G to the W of tau. That was the commitment to W in the first proof. And it sent, like the, what I had said, I'm trying to show that you can take these two evaluation proofs, one claiming that P of R equals V and the other claiming that P of R equals V prime, and you can break the strong Diffie-Hellman assumption. So given the two evaluation proofs, the first proof contains G to the W of tau. That was the commitment to W. The second proof contains G to the W prime of tau. Of course, the two claims themselves contained V and V prime. And so you can compute this quantity in the exponent, right? So the two proofs contain all of these elements. So you can, just take the first group element, multiply it by the inverse of the second group element, and then raise that to the power because the proofs contain V and V prime, right? And that's just going to equal G all in the exponent, W tau minus W prime of tau over or divided by V minus V prime. And this equality says that exactly equals G to the 1 over tau minus R. And so we successfully managed to identify R comma G to the 1 over tau minus R, thereby violating the strong Diffie-Hellman assumption. So yeah, in summary, I guess it wasn't sketchy, it was formal, but just the intuition is that these equalities are getting checked in the exponent. And so it's easier to reason about things, I think, if you just operate directly on the exponents and get rid of the group elements that are the base of those exponents. But anyway, yeah, so the two opening proofs sort of imply that the exponents satisfy two equalities, one per opening proof, one per evaluation proof. And the fact that they satisfy those equalities mean you can take those two evaluation proofs and actually solve for the quantity that violates, that you shouldn't be able to solve for efficiently if the strong Diffie-Hellman assumption is true.
Look at sources for this.
Okay, does that? I know that wasn't the best presentation, but hopefully it was not a complete waste of time. Does anyone want to ask any questions about that?
It seems like working on the server side and client side, it's just I'm having trouble communicating them with one another.
Okay, so maybe I'll just
it's more just about debugging
really briefly, what happens if you actually do want a polynomial commitment scheme, like how the security analysis has to go.
Be way more modern.
So in the I'm gonna be super sketchy here, but the algebraic group model
it's more about
sort of tells you I'm gonna be super hand wavy, but basically tells you in order
this is just easy to integrate,
to compute
it's doing friend requests.
A group element
I want to be able to send a friend request on one side and the other person gets notified.
In particular the commitment.
As long as that's in, I'm not going to do. I just want to know that works.
Committer wants to commit
so then,
to.
All right, now I understand how it works, and I have at least think of it like a limited demo.
The only way to
and then from there,
obtain that group element, the commitments, the committer,
you join, I join,
must have
then we start the experience.
known or chosen.
So the WhatsApp is, however you test
n values or n plus 1, I guess, C0 to Cn, such that the group elements that it sends. So the group element, the commitment to the polynomial, equals. So these you think of as just the coefficients of the committed polynomial.
The guy from Coconut.
So what's happening is, given the SRS, the SRS tells you these, positive powers of tau in the exponent. And so, the honest committer, what it would do to commit to a polynomial is, of course, it would take, the appropriate linear combination of those exponents, which it can do by just raising each group element in the SRS to the appropriate power, CI. And then multiplying the results together. And the algebraic group model, to kind of really butcher it, and I've never even studied the algebraic group model myself super carefully, but it basically says that's the only way to get to compute group elements in the group
you
is
want to
to
wait
take
until it's fully
like group
done.
elements you
But,
already
like,
know
that alone is impressive.
and, you know,
What
do
you
this
guys did, so
procedure of, you know, raising
there.
each one to some power and then
Nice
like
of him,
producting the results
you
together.
know, asking.
So another way of saying that
Yeah.
is
They're
like
interested in
the
people
only
who
thing
are
attackers
using
can
their-
do to like generate,
their stuff.
you know, new elements of a group
Mhm.
of the
Yeah,
group is
definitely
to
shows
take
initiative
elements of
on
the
their
group
part.
that they've
Like,
already
I
been
mean,
handed by someone
they're
else
great. They've been
and
updating
like
it a
take
lot,
linear
and I see
combinations
no
of their
reason for us to
exponents
switch
like
up
in
the
the
token up.
exponent, right?
And if anything, it's good because they're early, and like we're starting to
yeah,
learn what
so
it's are and
it's
gonna
sort
be
of
using
just
it a lot,
assuming
obviously,
that
so
the
we can like help
prover,
them
you
out.
know,
Yeah.
in order to compute the
Actually,
commitment,
you're
like it
helping.
must have had, you know, it must have known, had in its
Yeah,
head
sure. I
these
guess with the
coefficients.
track meshes,
Okay,
because that was
and you can
I
show
think there was a problem with the track meshes.
then that basically
Yeah,
to pass the
you're right.
verifier's check
But all right, so all I did was literally create,
you know,
like, a
for of the
special folder
evaluation
on source
proof
client, and so client is just a provider.
that you know, the
provider.
polynomial
This was pretty
given
weird to
by
figure,
these
but then
quantities that the
doing this,
prover knew.
sign in, yada yada. Server side is just simply this, and then
you know,
so
must satisfy
I'm using, for example, here in friend list,
P of
and then I
tau,
realized that
sorry, P of R,
oh, this is actually like a perfect reason to use
P of R
hooks,
equals V.
especially when we use it on when we're like playing against each other.
Yeah, I'm trying to
be
keep
so
this
much easier to use
discussion
hooks.
short. As a
Rather
result,
than
I'm
like
probably
have to
making
like
it just
redo setting up the subscription,
not very
adding the
clear.
events, doing the callbacks.
But
Right, so
okay,
we just made this, and all it is
the binding scheme
passing some initial
doesn't actually really
argument,
tell
right?
you.
So for here, it's just like friend data, and this is from the server.
It
And
says
then
the
you pass
prover
in
is bound
callback
to some
functions.
function. As soon as it sends a commitment, the prover is bound to some
So
function.
like for friend added,
but it doesn't tell you how
this.
to actually
for friend deleted,
in a
do this.
snark.
And then I
We
also
need to
have
show
request pending,
that
friend request
the
accepted.
prover actually knows
And
the
then
witness for the
literally all
claim
that's
it's
happening
making.
here
And typically the polynomial commits to is like some low degree
taking it,
extension of
getting
that
the
witness.
client,
So like the coefficients of the
client,
polynomial that it commits to
and then
should
from
basically
here,
tell you the witness for the claim that
subscribing
it's
to
making.
friends. So
So
friends
we
is
need to
the
be able to
channel.
take these, you know, polynomial commitment schemes
and then
like
I'm
binding
looping through
of them is like really not enough. You have to actually
like the
identify
callbacks.
like
You
the
figure it's like an
coefficients of the
object with
polynomial
the name
that the prover
and then
has
the
committed
callback
to.
function, I
So
guess.
there needs to be a knowledge
And then,
extractor
I'm just
that can
binding
actually take the
the event
prover
name to them,
and like
that
pull the
callback.
coefficients of the committed polynomial out of the prover's head, because those
Right.
coefficients tell
And
you
then
the
just
witness
clean
that the
it up
prover's,
afterwards.
you know,
Yeah,
claiming
so that's
using the
what's
snark
going on here.
to claim it knows.
And so it seems
So
like
if
it's
I just
working,
tell you
it's
that
connecting
the
at
commitment
least
scheme is binding,
to
you know, it's not clear how to
pusher,
actually
right?
learn
Like there's still two.
what the prover is bound to, besides
Well, let's
just
see
asking it at like, you know, every possible point.
there's
Hey, tell
four.
me, you know, P of R1,
Floating.
tell me P of R2,
Oh,
tell me P of
peak, that's not
R3,
four.
and having the prover
So
respond.
This is just sent to them.
This pusher
Now, if the
service
prover were
basically
actually
it
bound to a degree n
receives
polynomial,
the,
there's sort of a generic reduction
WebSockets
from
information
between
and
binding and
forwards it to the
extractability,
other
because if I
side.
tell
Is that
you
what it does?
any, you know, n
Yeah,
evaluations or
yeah,
n plus
I
one
think
evaluations of
it's-
a degree n
let me see,
polynomial
like,
through polynomial interpolation, I
Welcome to
just told
Pusher.
you the
Our
whole
hosted
polynomial.
APIs are flexible, scalable,
Right.
and
So
integrated
you
to
can
network
identify the
products, yada, yada.
polynomial
So I'm just
by
using
sort
channels.
of forcing the prover,
Right,
you know,
the
by
real-time
rewinding
features
it and
on
starting
your
it over
mobile
again or
apps
something like
using,
that, to tell you, you know,
Yeah,
like
so
n plus
just
one
all it
different
is
evaluations of the
allows
committed
for real-time
polynomial.
communication between
Okay,
servers,
but
apps,
you know, our initial
devices.
security analysis based on the strong
That's
Diffie-Hellman
all it is.
assumption
So it's like
did not
a way to
promise,
link
did not
the
guarantee that the
client to
prover
the
was bound to a
server,
degree
and
n
then
polynomial. It just guaranteed
the
that it was
thing is
bound to
about
some function,
Socket.io, I
which might
remember
be,
you would do
you
something
know, have
like,
much higher degree than n. So
well,
that
first let
reduction
me
doesn't
preface.
actually
The
apply if all
problem
you
is
know
right
is
now
function
the
binding,
other
not
client's not receiving.
binding to a polynomial commitment
Like I still
to an
have to
actual
refresh
degree
the
n
page.
polynomial.
Like I'm even
Okay,
logging
but
stuff
in this
not
algebraic
there.
group model, you
So
can actually
then I'm
show
wondering
the
if it's a
prover really
problem
is
with
bound to a degree n polynomial.
because
So
I'm using
basically,
localhost 3000. That like
yeah, you can.
it sends it to localhost 3000.
The algebraic
I don't
group
know.
model
Maybe you
just
have to
sort
spin
of
up
tells you that
like
there's some way
a
to
whole other
identify,
localhost
you know, the
to get it
coefficients
to
that the
properly
prover
work. I don't
used
know. But also
when it was
then,
committing to the polynomial,
on the server side,
and
like here,
moreover,
so
to
it's
pass
like,
the evaluation proof,
friend request
you can show that
the one that
you know
should guarantee
the
work is
polynomial
this.
given by those coefficients has to
Pusher.
have the
This is
appropriate
from the server.
evaluation.
Trigger.
But I guess another, I guess you can maybe
all
even
it is
omit
the
this
channel,
now that I think about it.
and then the event name, and then the body.
Yeah, once
But for some reason, I'm not seeing it.
I might be saying something a little bit wrong here, but you know,
So I
intuitively,
gotta look more
you
into
know,
that. That's it.
once
But
you know
yeah,
that
it's
the
simply
prover is
debugging.
actually
Like
bound
everything's kind
to
of
a
laid
3n
out.
polynomial instead
And
of
then
just an
once I know
arbitrary
this
function by a very
works,
high
I'm
degree,
literally just gonna create
binding and
like another hook, but this is gonna be
extractability
for the game.
are
I'll probably
basically
need
the
actually a
same for
couple
the reason
hooks.
I just said. Like, you know, as long as you can force the
But
prover
yeah,
to
let's
tell
do
you
that.
the evaluations at n+1 points, you can
So
actually
I'm gonna show
identify the whole
you
polynomial.
my
So
progress.
anyway, like yeah, once
So
once
it doesn't
you've
look like a lot of
shown
progress,
that
but it actually
the
is.
prover actually knew
Okay, so
you know,
Yeah, I believe
n+1
you.
coefficients that
this
it used to
this blue
produce the
box
commitments,
is the
and
real,
once I tell you that the scheme is binding, which we
the
sort of already
desk
showed, like those two things together
representation
should give
of my
you, like,
desk
you know, that
in
it's the
real
kind of
world
polynomial
coordinates.
commitment scheme we
Okay,
want.
that's why it looks
Waving my
like
hands a
it's
bit
all
and maybe saying something that's
right
not
on top
quite
of the
accurate.
floor.
And the last thing I'll
And
say
it has the
is,
shape that it has because
you know,
that's the
if
shape of
you,
my
you
desk.
know, I think
Wait, so do you have a
practitioners are
floating
very,
disk?
very
Or like do
comfortable
you have
working in
like
something
little
like the
pods at the
algebraic group
corner
model
that like
because
Yeah,
you can
this
navigate?
model
I,
basically
it could
does cover
also
like
be
all known
me
attacks
not being able
on
to.
like elliptic
I
curve
mean,
based you know, commitment schemes
when
and
I
stuff.
described the box
So you know, a
in the
security
room
proof
setup,
in this
maybe I
model
missed
does, you know,
quite a
at least
few
show that
inches.
like
The floor.
brand
I don't
new,
mean to cut you
wildly
off,
different
but another thing
techniques
I've
would be needed
realized, and I
to
don't know if you've
attack
taken this into
you
account,
know, the
is
commitment
that
scheme.
over time the
But
meshes in the room
if you
setup
don't like
change.
working in
I noticed that. Yeah, I
in
also
this
noticed
model
that.
that only reasons about a
Yeah, it's
limited form of
really
attacks,
annoying.
you could just
Really
make like a
annoying. But
very,
I don't
very
know
strong
how that will
cryptographic
affect you and if
assumption,
you're taking that into account.
which
But
has a
just wanted to add
similar
that.
I
flavor
don't think
to the
it's
algebraic
gonna.
group model.
It's
So these
important because
assumptions are
remember
called
that I
knowledge of
just take a
exponent
snapshot.
assumptions.
So all I do, all my calculations are based on a single snapshot.
Okay,
So that's all.
and
I mean, that's all that
yeah,
matters.
maybe
Is
I don't
that
want to say too much
snapshot
about this. It
taken
sort of, it has a similar flavor to,
at
you
the
know, well,
beginning of each
if the
session, like of each game, let's
prover
say?
can, you know, pass
I don't
some
know
check of the
how are you
verifier,
planning to implement that
then
part
the
because
group elements
Yeah,
it's sent to
I
the
was gonna do it
verifier, you
that
know,
way.
as
okay.
commitments
Because
must
remember
have actually been obtained,
it's
you know,
kind of
by
like
taking,
there's no point
you know,
of
n+1 values
storing it in
and,
the database
you know, applying them to the
because it
SRS.
would actually
And
just
then
be
those
better,
n+1
I
values
think.
must actually be coefficients of
For
the
well, for
polynomial
one,
inside the
we don't have
commitment.
to worry about like, oh,
So
we're
I'd say what these
storing
knowledge of
your
exponent
room
assumptions are
information in
doing,
that
though,
database, right?
is it's
So like that's an obvious.
it's
Two,
having the verifier do some extra checks
well, when the
that
game both starts, we're both
presentation
gonna
of
get
KZG
launched into the
commitments
WebXR
today didn't
experience.
have the verifier do.
So like we
I just
both need
sketched
to
that
be
really
in there and we'll
quickly.
be there the whole time.
So the SRS becomes
So
twice
if
as
both
big.
of us are in there,
So, you
then
know, for
like
every
we
group
have
element in
access to
the
each other's
SRS,
data, you know?
not only do you have that group element like
Like well
G,
we
but
could the
there's also
website
an
could then
extra
make it so each other have access to
piece
the
of
data.
toxic waste, in addition to tau, which
So
was
yeah,
a
that's
random
I
field
was planning
element. Now
on
there's a random
each
field
time the
element
game
alpha.
launches,
Um,
we
and
get the
so
track
each
messages, track
group
lines.
element in the SRS also
Great.
gets raised to
So
the power alpha.
that's how I'm
So,
going
you know,
to
G was in the
implement
SRS.
that.
Now
Okay.
G is also provided raised to the
Okay,
power alpha. G to the tau was
so
there.
the blue
Now it's
box is
also
the
raised
real
to the power alpha.
desk,
G to the tau squared
and
is also
this
there. Now raised to the
green
power alpha.
sphere here, this one,
And
it's
you know, the
that's the hidden object.
verifier, like
Okay,
any
in
group
real world
elements that the
coordinates,
prover
it's
sends
just
as part
behind
of the
the
proof.
desk, floating
Now, say the
in
prover, you
space.
know, previously would have sent,
So the
you know,
other
like G to the
points
W of
that you see
tau,
here
at least if it's honest.
are just
Now that also
the
has to get
translation
paired,
of this
or
box
you know, appended
to
to it,
the
G to
these
the
other
W tau,
coordinates.
you know,
You
to
see,
the alpha.
it aligns
Okay,
perfectly
and the verifier can
the
use checks. Can use pairings to check
axis.
that. I don't know if I just call
Yes.
this group
Okay.
element
And this green
G1 and this
sphere
group
here
element
is
G2. The
translation of the
verifier
real
will check
object
that.
to these other coordinates.
You know, it wants to check that.
Okay.
You know, the exponent to the first
Yeah.
is,
Could you
or sorry, the
explain that
exponent to
again?
the
Okay,
second
so
is the same as the exponent of the
these
first times alpha.
8
So the verifier will check that.
points here,
What is
the
it?
ones that are aligned
E
on
of
the axis
G1 comma G to
are
the
the
alpha
representation of the same
equals
desk,
E of G2 comma
but
G.
I
Right,
mean,
and that, so that's just confirming
Oh,
that
imagine
yeah,
that
I
whatever the
translated it
exponent of
yeah,
correctly.
G2
The green
is,
dot.
it's equal
the green
to
dot is
the
this
exponent
same green dot, but in
of
the new
G1
coordinates.
Okay, that
times
makes sense.
alpha.
Okay.
That makes sense.
Okay, and
So
the knowledge of exponent
what I
assumption
have
says
to do
the
now
only way
is
to
just
come up with
apply
two
the algorithm
group
that I
elements that
already
pass this check is
wrote
if
for Mina
you had
to
taken
this
a bunch
new
of group elements
set
that
of
you were previously
points
handed,
and this
each of which
object,
individually would pass the check,
because it's
and
already
you take,
aligned with the
you know,
axis.
like
Remember that
a linear
the algorithm
combination
I
of their
wrote
components,
You mean
exactly as I was trying
assume
to
that the
convey
box was aligned to the
in the
axis?
case of the algebraic group model. Because,
Basically, that's it.
it's always the case that if you take two group elements
the
that do
next
pass
step
some
Did you
sort of
use the
check, and you
translation
take a
from
linear
the
combination of them,
concordance? do
that
this?
their
Yeah, like how we
exponents,
talked-
that the
use
linear
the
combination
matrix.
will pass the check as well, right? Because
Okay,
like,
sweet, nice.
you know, if you
I
take
definitely want to
like
go, like,
you
it doesn't have
know,
to be now.
let's say your two
But
group
at one
elements
point, like
are,
how
you
exactly
know,
you
G
do
and
this?
G
Because
to
I
the
feel like this
tau.
really helps you
Um,
get a better
and
understanding like, through these
if
things.
you
Yeah,
look
sure.
at, you know,
It's actually
turn that
quite
into
easy.
G to
I
the
mean,
C1 plus
you just
C2
have
times
to
tau.
calculate
That's
the
what I mean by
inverse
taking the
matrix.
linear combination of
I mean,
the exponents here. The exponent here was
each
1 and the
object
exponent here
has
was
a
tau.
matrix that
And you
determines
take G to
its
the
position
alpha
in the
and G
real
to
world
the, you know,
coordinates.
alpha times
So in
tau,
this
and you
case,
take the
what I
same linear
did was the
combination of
opposite.
them, you'll get G to
I
the, you know,
translated
alpha
the object
times,
from
you know,
the real
C1 plus
world
C2
coordinates
times
to this
tau,
other
you
system of
know, which is
coordinates.
just, you know,
So
this
it's
thing to the alpha.
basically applying the inverse
And so the
matrix.
power knowledge of exponent assumption
I can
is telling
explain
you
that
like the
later
only
if you
way
want.
that you can get group
Yeah,
elements that
the
will pass
whole
this
matrix
relationship where the
really.
exponent of
Mm.
1
I
is
still
the
don't
exponent of
get
the
it,
other
but
times
yeah.
alpha,
For
is
all
to
intents
have
and
done this,
purposes,
to
like
take,
I
you know,
understand conceptually
pairs of group
how
elements that
how
already
you're doing it.
would pass the
Yeah.
check
But
and,
basically,
you
it's
know,
that any
do this linear
translation
combination
and
thing
rotation
to
of an
their
object in
exponents.
space
So
can
it's
be
a similar
represented
flavor
using a matrix.
to the
Okay. So, for example,
algebraic
if you want
model,
to
but it
represent
has it increased the
translation, just
the cost
translation, not
of the commitment
rotation,
scheme because the
you
SRS doubles
can
in
do that
size,
with a vector.
and you know the verifier
Okay, for
has to
example, if
do,
you want to
you know,
move
these
this
extra
desk
pairings.
to another position, but
So
keeping
if
the
you
same
look back
orientation,
at old
just translation,
snark papers,
that can be done with just a vector.
you have to go
On the
back
other hand, if
pretty
you
far,
want
I
to
guess.
keep
You'll
the box
see
in the same position, but you
SRSs
only want to
with these
rotate it,
extra things in them.
you also can do
I
that
think like
with
early
just one
versions of
vector
Zcash did
that
have,
represents
you
the
know,
rotation.
these extra
But if you
group
want to
elements in
represent
their
both
SRS
changes,
with these
both the translation
powers
and
of
the
alpha in
rotation,
there. And eventually,
you
I guess I don't know the
you're gonna
exact
need two vectors,
developments,
right?
but
those two
you
vectors can be
know, people
combined
got
into a
comfortable
single
with the
matrix.
generic group
So
model
the
and the algebraic
matrix
group model, and
basically is a
without
representation
the
of
extra
the
checks, these
translation
things
and
are
the
secure
rotation
in those
of an
models.
object
And
in space.
now I'm pretty sure with
Okay.
KZG commitment and
How is
Grow16
it
and stuff,
again? Like I didn't take
you no longer have
matrices
those
in
things
school.
in the exponents.
So I really
Yeah, I
don't
think
have that great of an
Grow16, I'm quite
understanding of it. Like,
confident.
how
It's
is
been a
it
while
written
since I
now?
looked at it, but
Like,
you
what's
know,
it make?
it's
Is it like
analyzed,
a
its security is analyzed in
like
the
would it
generic
look
group
like a
model or
chart,
something,
like
and
with
I'm
3
pretty
columns,
positive
2 rows?
it
Yeah,
doesn't have
actually,
these, you know, G to the
that's
alpha, G to
what
the
a
tau to
matrix
the
is.
alpha,
In this
and so
case,
forth
Like
in the
I've seen
SRS.
them. Like I've seen what a matrix is, but like I don't know how to
Yeah,
add
so
them. Like I don't know
hopefully,
how to
you
multiply
know, you
matrices. Like
probably
I don't know how
would
to
have been
use
better
them.
off today
Yeah.
So like
just
that's
leaving
why
after
like
I
I don't
presented
see.
how
I
KZG
don't
commitments work.
understand
But
technically how
hopefully it was a little bit helpful to
by
see
combining the
the actual
rotation,
security
the vector.
analyses and to
Well,
see some
isn't also the
discussion
rotation
of
a Euler, not
you
a
know, the
vector?
subtleties that come up. You know,
What?
again,
A
if you
Euler?
sort of use
Euler?
sort of what are
Yeah,
considered mild standard
EYEU.
assumptions,
Yeah,
then you know
EULAR.
the version of
Yeah,
KZG
but I
that's
think
most
it can be
performative
also
and deployed
represented by
today is
using
sort
a
of only
vector. I
known to
think.
be
I'm not
function
sure.
binding and that's not
Okay.
what we actually want from
Okay,
a
but I mean,
polynomial
it
commitment
seems like
scheme. We
you're
want a
doing
much
it,
stronger
so it must work.
property of
Yeah,
it
yeah, it
With
that
the
you're
vectors.
actually
Yeah.
bound to a degree n polynomial.
Yeah.
Yeah,
And
because
so to actually
in
show that,
3GS, Euler
you
angles
either need
describe a
to do the
rotational
security analysis
transformation
in an
by
idealized model, which
rotating an object
people
on its
are
radius
comfortable with these
axis
days,
and
or
specified
you
amounts per
make
axis
the scheme more
in a
expensive
specified
and still
axis
make a
order.
pretty strong assumption.
Iterating
A
through a
lot of
Euler
cryptographers
instance will
don't like
yield its
knowledge of
components
exponent
x, y,
assumptions.
z
I
like
won't get
order
into it since
as
I've
like
been
the
babbling for so
parameters in
long,
the
but
corresponding order.
they're something called
Yeah,
non-falsifiable,
actually, that Euler
which is just,
is
you
a
know, it
vector
means they're like
because
not of
it
the
has three
flavor
components.
that you know,
Yeah, I
theoretical
think it's just the arguments that
cryptographers
go
tend
into
to
it are
like.
different.
I'll
It's
sort of
like
just leave
the
it at
x
that.
is the angle.
Yeah, so that's
Like it's
KZG
based off
commitments.
of
Again, people
if
really
you
like
wanted
them. They're very
to
popular,
transform
mainly
a
because
degree to a
the
Euler,
verifier costs
I think
are
you
so low.
do
They're really the lowest
the
around.
degree
They do require
times
pairings. They do
pi
require
over
trusted
180.
setup. Those are some of the
Radians, that's all
trade-offs.
radians.
Okay, so that's
Yeah,
all I
are
had to
they
say
not?
about
Am
them.
I
Next
correlating
week,
them? That
I
they're
needs to
not
be an off
similar?
week. I have a
You
conflict,
mean
but I think after that, I
okay,
shouldn't have any
so
conflicts for a little while.
that's an angle.
So if
and
you
it's
have any
expressed in
questions,
radians.
feel free to stick around and ask them.
What do you
Otherwise,
mean?
Yeah,
thanks for bearing
exactly.
with
Is
me
the
today.
rotation
And
that?
yeah, I'll see
Yeah,
you in 2
yeah,
weeks.
the
And
rotation can
you've
be
also also feel free to reach out over the Discord. I'll try to monitor that. Thanks a lot.
Angle.
Yeah, so this is where it clicks. I mean, maybe this is
Have a
like
great
a deeper
weekend.
discussion that we'd have to like really go into or just do research on. Because that
So I
like
had a
the
question,
whole
actually.
transformation of two vectors, one representing the position. I mean, the new
so,
position, and one representing the new
so you're just
rotation,
mentioning like
combined to
comparing
matrices.
this
like
AGN
I just
with
don't see that connecting.
AGM model
That's fine.
with
That's fine.
Me neither. I mean,
this knowledge of X-Men
I don't know how to do that manually.
assumption.
I'm
and,
doing it using Trija. Yes.
So you said the knowledge of
see your
X-Men
Yeah.
assumption, requires making the scheme a bit more expensive. So yeah,
And rubbing off on
modifying
you,
it a bit.
blackboxing. Don't know how to do it.
So
but
is it
we make it work.
so is it the case that
Yeah.
the
Okay.
that the AGM
Let me see.
is it the case that the AGM model
So,
is
here
a stronger assumption than the knowledge of X-Men,
I think they're.
but just that.
Sorry to cut you off. Go ahead.
No, just gonna is it a more expensive? Is a strong assumption because
the matrix
it doesn't involve needing to
from the
modify the scheme,
actual data from the.
but nevertheless, I think
Okay. So
I think you said that cryptographers are comfortable with the stronger assumption. Is that the case? Or?
Okay.
Yeah,
Comes
I think
from logging
I'm
out.
not 100% sure that
from the
something secure
Okay.
And that is enforced.
under
Enforced.
the knowledge
Yeah,
of
is it
exponent
good to enforce?
assumption is automatically secure
Like, what is each?
in the
what does
AGM.
each
That
element
there's like
mean?
a
Oh,
like a
like,
strict formal
in this
relationship
case,
between them.
This is a 4x4
but,
matrix. So these are 16,
that may
16,
well be the case.
elements.
It
And
feels like
if
it
we
should be
were
the case to me off the top of my
visualize
head.
this in matrix form,
Um,
it's a 4x4 matrix.
but at a minimum, qualitatively,
So
people
these first
consider
four are the
the
first column.
the generic group model
This
and
is the second column.
people consider the generic group model, I
third
guess,
column,
like kind of
and fourth column.
the most aggressive
Okay.
But for
setting in which to
simplicity,
do a security
they are
analysis.
represented
So
as
when
a
you're
single
like
vector,
looking to
I mean, as a
squeeze
single array.
maximum possible performance,
Okay.
Okay. Yeah,
that's the
how,
setting to do your
the like
security
polygons
analysis
are
in.
set up.
It sort of
Okay.
captures all known attacks,
Yeah,
and
exactly.
it's sort of
Exactly. It's just an array.
the minimum
Here
model
I
to
create
capture
this
all
local
known
metric
attacks,
variable,
something like that.
and it's of type.
And then they
matrix
think
form.
of the AGM, which again, actually,
Okay.
there have been some papers showing that they're technically
then
incomparable, but I
I
think qualitatively, like a
Import
security
those-
analysis in the
those
AGM,
numbers from
my
this.
sense is people consider that a little stronger,
array.
like
That's
like
what I'm doing
better
here.
to have than a security analysis in the
This
generic group
basically this,
model.
like turns
There are some
off the
subtleties where
matrix
there are a
auto
couple
update.
different variants of the
Remember
models that people look
we
at and they
talked
have
about this?
different powers and stuff.
Yes.
But,
Yes.
it's not
So
really important.
Why did you need to do that?
Yeah, so
I'm not sure.
without giving a
That's-
completely
I'm not
precise
sure.
formal answer
But
to
you know
your
you
question,
had to
I
do
think
it.
qualitatively
Exactly.
you're
Okay.
correct
Okay.
So
that
here I apply that matrix.
people consider
to
these
my
generic group and
table mesh,
algebraic group
to
models
my
to be
actual mesh, the
the
best, okay?
most aggressive
Okay.
That
setting to
basically
do
moves
the
it
security analysis
to
in.
the right position.
That
to
yeah,
the
so like sort of the
real world
implications
position.
of the security proofs for security
Okay.
are
Just
weakest
applying the
in
matrix
terms
to
of
the mesh.
giving us confidence that the
Okay.
snark is
Before
actually
this line,
secure and not attackable.
The table is
but
not
at the same
in the
time,
real world position.
It's not meant to
After
disparage
this
models.
line,
We really,
the table is now
have never
in the
seen anything that
real world
is
position.
like secure in the AGM, but then there's like
After
an
this
actual
other
attack on
line,
it, right? The whole point of this is
basically
that
what does
we don't really
takes
know
the matrix
attacks that
and it
sort of are not
decomposes it
capturable
in these
in
three,
these
elements.
models. Is that helpful?
This is the vector position.
Mm-hmm. Yeah, that's
this is
helpful.
The scale vector, which
had another question
because
about
the matrix can also include scale.
about the comment you made about
It's not
about
just
the scheme
translation
being
and rotation.
binding,
It's also
but
scale.
only function
So the
binding.
same
So
matrix
so
can codify
that
the
means
three
like we don't
at the same time.
know the thing being
And this quaternion is
being committed
something-
is
I don't understand
is a
exactly what it is,
polynomial.
but
Yeah.
it
We don't know whether it's a
basically codifies the
polynomial that's
rotation.
being
Okay?
being bound
Yes,
to.
yeah.
It's only that it's a
So
function.
this
Yeah.
is a three-element object.
And
a
okay,
vector.
and sorry, just
This
to finish
is
off
a
the question, and
four-element object. That's why it's called
and then
quaternion.
yeah, and
It
these
codifies
are
the
and these
rotation,
approaches that you're
this
talking
is
about
a
now
vector, a scalar.
is to
No, it's not a scalar. I'm sorry.
is not just
actually a vector
to is not
because
just to
it has-
show that
It-
the
Yeah,
thing
it's
being
just like
committed
1,
is
1, 1,
a
let's say.
polynomial, but it's a stronger
you
thing, isn't it?
You can
Because it's
scale
saying
an
that,
object in different.
it's also
dimensions,
kind of establishing that the
Okay.
committer knows
Finally, I
knows
add
what
the
that
table to
polynomial
the
is. isn't
scene.
it?
Yeah, so I do
Okay,
think,
so
and I should
basically,
either write it down
This
or
is
talk to
makes the table
someone else
move in
that
space and
is
rotate.
a little
Yeah.
bit more
When you
comfortable
apply
with
the matrix to the
knowledge, intricacies
Okay,
of
and
knowledge,
then
soundness, security
decompose
proofs and stuff. But I think
I would
that
think that would be composed.
binding to a degree
So
n
decompose,
polynomial
what
is like
exactly is
equivalent to extractability
okay.
of the
Like you
polynomial
hover
just
over the word
by
decompose.
polynomial interpolation,
I don't
right?
know if
Like
you have any
given any snark
Yeah,
prover
the mesh
that's using
has
polynomial commitment
elements,
scheme,
I mean,
it should be
attributes
possible.
called
This is the sort of
position,
thing I haven't
pattern,
worked
and
through all the
escape.
details of, but it should be
But
possible
they
to
are by
like kind of
default,
force
when I
that prover
create a
to give
matrix
you,
like this one,
you know, n different
when I create
evaluations
a mesh
of the
here,
committed
like
polynomial.
this,
And then
with this,
once you've done that, you've extracted
code,
the polynomial just
the
through
mesh
interpolation.
has those
So
three attributes null.
I think
I
in
mean,
the
they are
case of
null,
univariate
position, pattern, and
polynomials,
scale.
I think
If you apply
it's not
the
actually
matrix to the
stronger what you
mesh,
just said. They're just
those
they're the same notion in
remain
the end.
null.
Maybe there's some
only
overhead
after
in
this,
the runtime of the
line
extractor or
that
something
those three,
potentially. But these
attributes
these
are
knowledge of exponent
calculated
assumptions and the,
from
you know
the
what's baked into
matrix.
the AGM, they
Okay.
don't.
Okay.
People tend
Yeah,
not
actually,
to
I
be
think
quantitative
it's optional.
about, you know, they tell you there's
It's
some
just
extractor that will
you
pull
need
these
this
coefficients
just if
out of the
you are
prover.
going to call
They
the
typically don't
position, the
say much about
pattern,
how efficient the
and the
extractor is,
scale
besides that it's polynomial
directly.
time anyway. So
And I
they're
What
sort
you
of
do.
not
I do that actually.
telling you all that much
Okay.
about the, you know,
Let me
precise
see
efficiency of
what
the
I do
extractor
there.
anyway. So I'm not
So
really too
that's a
worried
way to
about
directly then change
sort
the
of, you know,
position,
overhead
criterion, and
in the
scale through the
reduction
matrix.
from
So
binding
like it's
to
in sync.
extractability, you know,
You mean this?
in the extractor sort
Yeah,
of having
like
to
you
rewind the
said, you
prover
do
and
use
run
the
it again
position,
to get n different
criterion,
evaluations of the
scale
committed
on, well,
thing.
maybe not scale on
Sort
the
of seems
matrix,
these
right?
I'm pretty sure these
So
knowledge of exponent assumptions
that's a
tend
way
to
to
try to
change it
avoid
directly on the
making
matrix.
overly
Yeah,
strong
you
rather
can
than
assumptions about
directly change it on
how
the mesh,
fast is the
and it
extractor
keeps
they're
the
assuming
matrix,
exists anyway.
and
Where do I
the
want to go with that?
mesh in sync.
I think if you
Uh,
change any of this directly,
Yeah,
it
so
will also change the matrix.
where I actually myself
Because
don't
the
know an
matrix is a
equivalence
function of
between
these three.
binding to a low
Yeah,
degree
yeah,
polynomial and
no, totally.
extractability
But
is
so
in
without addressing
multivariate
it, so if
cases,
you then
because
change it on the
with
matrix, it also changes
like
on
say
the mesh.
multilinear polynomials,
Yeah.
an
Any change
interpolating
to the
set is
matrix
highly
changes
structured. It
the
has to be like
position
a
of the
product
mesh.
set basically.
Okay, that
So
makes
it's like
sense.
0,
So
1
that
to
allows you to
you know
then,
number of variables
because
or
by
something.
default, if you just
And
like
so
create a
you
mesh
actually
with
do run
geometry
into
and
issues
materials,
in the
you could
reduction
then
from
add the
binding
position to the mesh,
to extractability,
right? But then
because
if you need
while I
like, let's
think
say,
you
more
should always be able
complex
to, you know, through
orientation, like
rewinding,
rotation, position, movement
force a
based off the
prover
matrices,
to tell
you
you, you know,
need
like a pretty
to
good number of
decompose
evaluations of the committed
those
polynomial. I don't think
into a
you can force those
matrix.
evaluations to necessarily be
So then
over
when
a
you
product
adjust the
set.
matrix, it will
It seems like
automatically
the
adjust
prover
the
could
position
just
on the
sort of,
mesh because
you
those
know,
become one and one,
like
right?
typically these
Am I
extractors are
thinking that
supposed to work
correctly?
even when the prover
Okay, so if you
only,
don't,
you know,
if I
succeeds with
point
some
this out,
non-negligible
the
probability.
table
So
will
there are
still be
probably a lot of
translated
evaluation
and rotated.
points where the
Okay.
prover might just be like, sorry,
This
I'm
is
not going to tell you
just
the
to
evaluation
fill
here, and like
these
you have to
attributes
extract the
inside the
polynomial in my
mesh
head
object.
anyway.
Because
And
first,
so
those
it
are
might,
null.
it feels like it could,
So after
you know,
this
just sort of
code,
fail
after this
on,
line executes,
you know, enough points that you're
those
very
three
unlikely to force it to
attributes
succeed on a very
of
structured
the
set of points.
mesh object
And so there
are
does seem
now
to be
populated with information.
an intrinsic difference
From the
between
yes.
like multivariate and
Okay.
univariate
So
here,
it's
where
not
in the
necessarily to
univariate
be there.
case,
If
like
anything,
any
though,
big
it's more of
enough
a utility
set
kind
is an
of.
interpolating
Exactly.
set, whereas in the
Exactly.
multilinear case, it's not the case.
Yes.
Okay.
So yeah,
Okay,
sorry for
so,
the rambling answer. And I really should have
that's
one of these
how
discussions
the
I hope
translation
this is
works.
also
you know,
helping you, by the way.
other
Like, understand this more
cryptographers
than just
to
for
make
me.
sure I'm not
Yeah,
saying
yeah,
something like
absolutely,
really
yeah.
silly. But that's my
Okay.
current
So,
understanding of the situation here. Was that a little bit
So
helpful?
now I have the matrix.
Yeah, it was.
And
Thank you.
Let me see what I'm
So it
doing
may
here.
it may well be that.
Okay.
Okay, so I wasn't sure if I completely got your first point. So is it for at least for univariate
the red
polynomials,
points
maybe
at
just
the vertices of
the fact that it
of
is
the
binding
table.
under a
That's
strong
basically what
Diffie-Hellman
it does.
assumption
And okay, so
is enough for it to
No, sorry,
guarantee that it will.
I don't think so. So strong Diffie-Hellman
array
alone only gives you function
comes
binding.
from the actual table
If
mesh.
it in a magical world where it also gave you
so here,
not
what
just
I'm
function
doing
binding,
is
but
I'm
actually
taking
binding to a degree
the
and
array
polynomial,
that is,
then I think it would automatically
I
be
think it's
extractable in
8
addition to
times 3.
binding.
It's a 24.
Okay. But unfortunately, strong Diffie-Hellman alone only gives you
It's
function
this
binding.
one.
It doesn't say that the thing
This
it's boiled
one,
down to
okay.
is a degree and polynomial.
And this basically converts
So
it
to get the prover
a new
bound to a
array,
degree and polynomial, you need to go
an
to
8-element
both
array where each element is a
these
vector.
stronger assumptions or idealized
That's what I'm doing
models
here.
and or
And
modify the
then
scheme.
I take each of those
But once you
vectors
do either of those things
and
or
I
both of those
apply the
things or
matrix
whatever,
to each of
you really only have to show is
And
what I'm
then
claiming,
I display
although
the,
I'd never run it by anyone before.
on
I
the
think
scene.
you only have to
This
show
function
that it's
basically
binding
takes a
to
point,
a degree n polynomial,
creates
and
a
I
mesh
think you get
with
extractability
certain
of that
radius,
for free from
and
the
applies
binding,
a
once you know
certain
that the
color,
proof is bound to
and
a degree n
displays in
polynomial
the
instead of
scene.
just an arbitrary function. However, these
So
analyses
basically,
Okay.
just
here
sort of
I am
naturally give
rendering
extractability
the
from the gun
8
anyway.
vertices
So there's really no
for
reason,
the,
That
there's no
function,
need,
Tony,
like
you
the actual
created just for
analysis
your
doesn't
point.
go through that indirect thing of first
yeah,
show
I created
binding, then show,
Okay.
you know, that
And
binding
then all it
implies
goes is
extractability
okay, yeah.
in
Okay, that makes
this,
sense.
you know,
it.
setting.
It
They just
creates
directly,
a
the
mesh,
analyses just directly show extractability. Is
and
that
adds it to
helpful?
the
Does that make
scene
sense?
at a given point.
Yeah, that's
Okay,
better.
that
Yeah,
makes sense.
clearer. Thank you. Yeah.
Yes.
Okay.
Yeah, thanks for digging into
Okay.
that.
Now,
And the last thing I'll say
So,
is, you know,
okay,
like I
wait,
feel
one last thing,
embarrassed,
sorry.
like
On the apply matrix
that
4, so on line 62,
I'm qualifying
you're
all my
applying
statements, and you know,
on
like
each
myself, am
point,
just
you're
like
applying the
mildly
matrix
uncomfortable
of the
with
table, so this gives it the
the security
correct
proofs, like just a little
rotation,
bit.
or
I did see
rotation,
Pratush Mishra, who's,
position,
you know, one of the
and
authors
scale.
of
exactly.
Marlin,
Exactly.
Okay.
That's
from
what
which
I
I
did.
actually,
Because
you know, like my treatment
originally,
of
these
KZG
vertices
commitments and the
are
security
these
proofs
vertices,
themselves
and
is
these
like,
are
you
not
know, largely based on
in the real world
saying
coordinate
recently
system.
on Twitter
It's
that
in
he
the
thinks there might
relative,
be
I
some
mean,
like
in
subtle
the
issues in the
in
security
the
analysis in
mesh
Marlin.
coordinate system,
So
which
that
is
makes
this
me feel a
one.
little better that
Okay.
you know,
And
be that
then
the other
here,
cryptographers who have written papers, you know, that
let
went
me
through the
see what
security
I'm doing here.
analyses, still to this
Yeah.
day,
Okay.
you know, are
Okay. So
declaring them to be
here
subtle
I'm
and
taking the
possibly
first
even bug
vertex
prone. So
from the box.
maybe I shouldn't
Okay.
feel so
Which is
embarrassed.
this
I
one.
think these issues really are
This is the
subtle.
first vertex.
But ultimately, you know,
Okay.
the high level message is
And I'm
practitioners are fine
calculating
with, you know, the
how
algebraic group model
a
today,
vector
and we
from
do
the
know
origin
that KZG commitments are
to this
extractable
vector.
exactly as we want
Okay, so
in
that's
the
basically
algebraic group model without having modified the scheme as I
what I'm
presented it
doing here
today.
is I'm
And so everything is
translating the
great, and the
box
scheme is super intuitive, and
so
you
that
know,
one of the vertices
unless you're like a hardcore
is in
cryptographer,
the
you don't
origin
have to worry
of
about
the real
the
world
security
coordinates.
analyses.
That's
Just
what I'm doing.
understand this really beautiful, simple,
Okay.
intuitive
So
protocol,
I'm calling
and
translation
don't worry about the fact that the
the
security analyses themselves are
vector
not as simple and
goes from
intuitive
the
as the
actual
protocol
position of the
itself,
box
I guess.
to the origin. Okay.
Okay, so negate like the
All right.
constants.
Any more
Which again
questions?
basically is the opposite direction.
Yeah. If no one has
And this would be for
any other questions, I
let's
have
say the 3JS origin.
one other one, so
point.
not related to security proofs. I guess it's.
I'm
So
moving the box.
you didn't
This is like
mention
the world position origin point.
You didn't
Correct.
mention
Exactly.
the hiding.
That's the world.
I'm just
Yeah.
wondering, is there something to say about that?
With this, I'm placing the box
The
exactly at the
short
origin.
version is
That's what I'm doing here.
that
That's
hiding
why
is
you're only
actually
doing it for the
not
first
completely
one.
trivial with
exactly,
KZG
because
commitments.
once I do it for the first
you
one,
know,
after that, I just have
especially
to
to get
apply
perfect
that
hiding.
to all the other ones.
You know, I guess the
And
commitment to the
they will,
polynomial p is g to
arrange
the
in the
p of
correct position.
tau, and you know,
So this
I don't have
basically
too
is
much
moving the
intuition
box
for
to
this,
the
but you know, I guess this
world
is something
So-
that you
such
know,
that
like
one of the vertices from the box
a simulator
exactly
like
the
couldn't compute on its own if like p, you know, encodes a witness
And-
or something,
that
right?
makes sense.
Like
And then you're just adding it from where
you know,
the origin is.
while like no one knows tau, like the SRS still involves tau,
Okay, that
right?
makes sense.
So like it's
And
not
this,
trivial to be able to compute.
Here I'm moving the real
You know,
world
there is
object,
some tau
the
inside this
hidden
SRS
object
here, even if it's like
from
hard to
the
compute.
real world coordinates
so,
to this
you know,
new system of coordinates, where the box is
a simulator that
aligned
doesn't know a
to
witness is not
the
going to be
axis.
able to evaluate a polynomial
So the
that does
green
include the
object that was
witness, you know,
originally
at this
in
tau
some
that
place
was
in the
somewhere in
real
the
world.
SRS. So I think
After
like
this,
there is leakage
at the same relative
in the
position,
protocol
the
about
same
the
relative
committed
to the
polynomial,
box,
which in a SNAR
but in
context
the
would
new system of coordinates,
leak information about the
where
witness.
the box is
There's
at
also
the
the
origin.
issue that, you know, as I presented KZG
Does that
commitments,
make sense?
I had the prover sort of tell the verifier
I just gotta
like
look
P
it
of,
over for a
you know, the
second.
evaluation of P of R in the clear, and that definitely leaks information.
Okay, so that
for sure.
last
So you'd have
part,
that's
this part,
a major issue. You'd have to have the prover not
is what
send
moves
the evaluation
this
itself.
real world
You'd have
hidden
to
object
you know, hide the evaluation in
this
some exponent,
other-
and
this
if you
new
want
position,
perfect hiding or
relative
perfect
to the-
CK, you'd have
to
to
the
blind
box
it
aligned
and
with
then
the
deal with the
axis.
fact that the thing is in the exponent, which is not something I've thought about carefully,
So
and certainly not
this point
dealt
and
with
this point
in the presentation
are the
today.
same point,
And I know,
Just
I was
that
like
this
chatting with
viewpoint
the authors of Zeromorph
is it's,
recently. Zeromorph is an analog of
respect to the
KZG
new
commitments for multilinear
So
polynomials.
where is the
And
green dot
they
being
call it
formed in the
Zeromorph.
code?
I think
Like
they really,
which
really
is
care
it on
about
the
it being
points or
hiding.
the
It really
vertex?
needs zero knowledge. The authors
Like,
are
can you
from
just
the
go back to
Aztec
the code
project,
for a
and
second?
that's like a private roll
So
up.
that-
So it's
or
that one on
whatever,
line
and so
81?
ZK is totally essential
yes,
for
this
them.
is the translated
And
point.
I'm pretty
The
sure that
translated-
they had to do
translated
some,
That's the green
okay.
one.
some work
Correct. That's
to
the green.
get, like zero knowledge,
At the viewpoint.
variance of KZG,
Look, here
to
is-
make
this
everything
is the
work
key.
out.
This
So,
is the key.
yeah,
I'm
I guess
applying
what
the
I'll,
same matrix
the high level
to the
message
hidden
is,
object.
I believe you
now-
can make KZG hiding.
It's now in the,
I think you actually have to think about it somewhat carefully. If you don't want to introduce, significant overheads or whatever. I think you can make it hiding without significant performance overheads, but you have to be careful about it. That'd be my the short high level version of my sense of things. And I haven't actually looked into it enough myself to actually say all that much more.
For me to
than
understand things,
the
I
high
need
level
to see
message.
how it connects. and I
Is that
don't
helpful?
get lost.
Okay, and exactly
And
what?
so, and
Yeah,
you're doing a
thank you.
great job explaining. Like, don't get me wrong. Like, you're doing
Yeah, so
phenomenal. I just
I'm
don't
not
understand
totally sure a
matrices enough
reference to point you
understand
to
how,
if you're
like,
interested
it
in the
works,
details
that
of making it
works.
hiding, but
You
like
know?
certainly you could look at
Like, you're doing a
Zeromorph,
really good job there.
and
I know
hopefully
more now than I
there's
know
some, I don't
Okay,
have it
but
paged
are
in, but
you
hopefully there'd be
understanding
some
the
decent
big
discussion
picture?
there, or at least a point or two.
Yeah.
Some
The
other
big
paper
picture
that
is
made
It's
sure
just
everything
the
was hiding.
intricacies
Off the
of
top of
how
my
it's
head,
done.
Yeah, exactly.
I
exactly.
don't know.
It's like,
I don't
have a
remember
deep
if there's
understanding.
discussion
I
of
think
this
I'd
in the
be able
Marlin
to do
paper.
something.
There might be that'd
Manipulating
also be
matrices,
it's a great
but, like,
exposition
I
that'd be
wanna
worth
understand
having a
how
look
it
at
works.
if
But do
you
you understand
care
This
to
is
get
why?
into the
something that I
details.
feel like I gotta
And again, I don't know the
understand.
details myself
definitely. If
off
we are
the
going to,
off the
if
cuff.
we are going to work with 3D.
Mhm.
That's
Yeah, like, I have
When
that.
you,
You
I mean,
have
when you
to.
refer to hiding here,
I also
you
have to
mean
understand it.
perfect
better.
hiding, do you, or does there?
Okay,
do
but
you think there's
you
Yeah.
do understand why I'm
difference,
doing all
with
this. I
comput-
mean, why I'm moving the box
hiding?
to
Well,
the
so typically,
to align it to this axis.
typically
and is that
you
clear?
can always make things perfect
Well, yeah,
hiding
'cause
by
I
just
assume then
like
you're
rather
gonna
than
do
committing
the same
commitment
thing for
being
the
unit
sphere.
p of tau, right?
Uh-huh.
Like
Exactly.
And then
the
you're just going to
you
compare
could
it to
typically
each
you
one.
can
So
always
essentially,
blind
you're
it
gonna
and have
loop
it not
through
really
each piece of
change, make
furniture.
any life more difficult
And
for,
then if
for
it's
you.
in there,
So if
like,
the
if
committer
you're
picks
going
a
to loop through
random
each piece of furniture,
exponent,
do exactly what
let me
you
just
did,
call it r
bring it to
prime
the
here,
local origin,
and multiplies what I
for
said
the
the
sphere,
KZG commitment
you don't
was
have to
by
do
g
that
to
every
the r
time you do
prime.
it once.
Right now,
And then
this
you
is
see,
a
is the
uniformly
sphere
random
inside
group
of it?
element,
If not,
regardless of what
Exactly.
ain't going to
p
next.
is.
If
Like
it
no matter
is,
what this is, once
essentially,
you multiply it
just
by g to
Yes,
the r
that's the
prime,
idea.
it's totally random. And so that's typically how you would make things
that makes sense.
perfect zero knowledge. If you don't
That
have the
makes sense.
blinding factors,
This has been
they're
so
often
useful.
like
I mean,
computational zero knowledge anyway.
This is
Just
one of
because
the
discrete logs are hard to
3S,
compute, and like if I,
basic
so
exercises.
sending you p to the tau and the exponents, shouldn't
Oh, what do
really,
you mean, to
if
do
you're
something like this?
computationally
Yeah.
bounded, shouldn't really tell you anything about p of
I
tau
mean,
itself because it's like hidden inside the exponent.
3JS website has a series of
So,
exercises.
I think normally when
So
people care about
I began
ZK
with
and
the
Snark
basic one,
land,
the one that just
they'll just make it perfect ZK
creates
and
a
it won't
rotating
really
cube
increase the
in
cost of
center
anything.
page. And I
But
built
it
from
does
there.
increase the conceptual load for
Okay.
sure. Like,
It's been very
I think
useful to
various
visualize things.
Yeah,
various
once we slow
protocols
down
just
a
get a
bit,
little more grosser when you have to
I
deal with
gotta
these
do
blinding
stuff like that.
factors. Yeah, is that enough?
Yeah, like
hand
working
wavy
with 3JS
discussion?
like
Yeah.
raw
Yeah.
in a
Thank
raw form.
Yeah. Yeah, and I normally
yeah, I mean, I did
I
that.
think in every paper I've ever
The thing
written,
is,
I just
I just
haven't
don't
worried
like about
ZK,
doing that is
and
because I don't like working with
I'm just
classes
like
and React
comfortable
apps.
that if I cared enough,
Because that's
I
all
could
3JS is.
make it ZK
like, the
with
basic
minimal performance
3JS,
overhead, and
it's
also I
classes.
generally think
I
recursion
think
with
in class,
Snark
like you're kind of like adding
is good
when you
enough
use
these days
scene.add,
that in most
right? Like the
settings
scene's a class.
you really just have like an automatic
It's just when it
ZK-ifying
comes to
hammer
like building like
by
reactive
don't worry about
applications,
ZK, take
it
your
makes
final
sense to
Snark
do
proof,
it,
it's not ZK, just
using,
compose
like,
one last
React
time with something that is
Fiber.
ZK. Then
Right.
someone else like the Planck authors or something have
So
done the
what
suffering
exactly is
of making
React
sure
Free
that
Fiber?
Planck has a ZK
It's like
variant.
React
So
Free Fiber is
just
essentially
apply that thing
3JS,
at the
but
very
in
end
React
as
format.
one final
Okay.
layer composition, and now
I've-
I literally
you
just
know,
never have to
you've
think about it
seen
ever again.
how,
That's largely my
like
perspective
in
these days.
MetaGallery, I got better examples in MetaGallery, but on how I added each mesh,
All
let's
right.
say each piece of
Any last
furniture.
questions?
Right, like I was calling track mesh, which is coconut.
Okay, well, thanks
but I'm
again
gonna
for all
put
the
in
great
just using,
questions
like,
and for sticking
primitive.
around to the
And
end.
that
And
essentially
again,
means it kind of just be
you know, for
anything.
tolerating the ramblingness and so
But
forth.
then you apply, like,
So again,
buffer
next week's an off
attributes to
week. After
it,
that,
right?
I
So,
think we
like,
come
all
back
the
and
rules
we'll
are the
talk
same.
about
It is
recursive
essentially
snarks.
1-to-1. It
And
is just a
after that,
different
Nova,
syntax.
and then
Okay.
That's all it
probably
is. It's a different syntax.
hashing-based polynomial commitment schemes like
Okay.
Laharo
That's
breakdown
more
Fry.
like
And then we might
React.
wrap up, but we, you know,
Yeah,
I
exactly.
could keep
They
going
just
for a
make
little
it
bit. We could
React
discuss
format.
Dory or something like that.
Like they have
Yeah,
hooks
so
to get
looking
the
forward to
frame.
seeing you in a couple weeks.
Each
Have
frame,
a great
they've-
weekend and week in between.
It's
till
just,
then.
yeah, it's literally a ported version of 3GS
Thank
into
you.
React.
Bye.
Yeah, bye.
Like, that's why it's so
Thank you, Jason.
popular.
Cheers.
Because people use
Everyone,
React all the
bye.
time, you know? And so, like, if you're building an application, it makes sense then to have your 3D renderer, i.e. 3GS, be in React as well.
Mm-hmm. Yeah.
But yeah, okay. Thank you for explaining that.
Yeah, anytime.
At least from a high level, that makes sense. It does make sense. I wonder if there's, like, good sources on, like, matrices